Hello, everyone. In this small section, we will discuss the hypothesis of Louis de Broglie that has been put in the year 1924, in which he stated that all matter is showing nature, wave-like nature, associated with wavelength and frequency. Let us recall the dual nature of light, where light can be considered to act as wave, especially in the known three phenomena I meant diffraction, interference, and polarization. Where we associate wavelength lambda, which is equal to c over f. And on the other side, light also has a particle nature shown through the phenomenon of photoelectric effect. And in this case, we consider that light consists of a packet of energy of electromagnetic radiation that are called photons. These massless particles can be associated with a wavelength lambda, which is equal to h over p, where p is the momentum of this photon. As I'm mentioning here that we cannot replace P by m times V, because photons are considered massless particles. Back to the hypothesis of de Broglie, where he, on the contrary, he proposed that particles, in their turn, are acting also in a dual nature, where particles sometimes or can be considered to act as particles or to act as wave. So particles can be considered to have a particle nature, normal particle nature, with a normal kinetic energy, half mv squared, and a normal momentum, mass times velocity, or they can be considered to act as wave. They can be associated with a wave-like nature with a wavelength equal to h over p, where we can replace p by mass times velocity. So in this case, lambda is equal to h over p, and it is also equal to h over mv. Combining these two natures to come out with a de Broglie wavelength in terms of the kinetic energy of the particle, as we see here, kinetic energy is equal to half mv squared, or I can write this as 1 over 2m times m squared v squared, which is simplified to p squared over 2m, and therefore p squared or p is equal to square root of 2 multiplied by the mass multiplied by the kinetic energy. Replacing p by this expression, and we come out with the de Broglie wavelength lambda, which is equal to h over p, or h over square root of 2 multiplied by the mass multiplied by the kinetic energy. Like, for example, let me talk about a bowling ball in this example. So consider a bowling ball of mass m, which is equal to 2 kilograms, and moving at a speed, say 6 meters per second. As I said, that de Broglie proposed that all particles or all matter has a wave-like nature, and that the equivalent wavelength was later known as de Broglie wavelength. De Broglie wavelength is given by lambda, which is equal to h over p, where p is the momentum of this moving particle. In this case, h is equal to, lambda is equal to h over mv. Knowing the mass and knowing the speed of a particle, we can find its wavelength. Regarding our example, lambda will be 6.63 times 10 to the negative 34 divided by the mass, which is 2 times 6, and on calculating we get so 6.63 times 10 to the negative 34 divided by 12, and the answer is 5.5 times 10 to the negative 35 meter. And it is clear why we cannot for sure see this wave motion of a bowling ball. It is just because the wavelength is extremely small, as you can see here. The biggest evidence for the wave nature of the particles, or that particles are having a wave-like nature, was shown by scientists later during the process of diffraction of an electron beam. A scientist called Davison ejected an electron beam through a crystal, and he took a clear image that shows that electrons are undergoing diffraction. While, as we know, diffraction is a characteristics of waves only. So this was a good and big evidence that particles may be moving in a wave nature, or maybe having some wave characteristics like a wavelength and other characteristics. The phenomenon of electron diffraction, as I said, was shown by directing a beam of electron against a sample of polycrystalline graphite. This is done in an electron diffraction tube, where electrons from a heated filament are accelerated to a high speed by a large potential difference between the negative cathode and the positive anode. The beam of electron passes through a thin sample of polycrystalline graphite. And while passing through this crystal, it has been the image or the emerging beam of electrons has been collected and displayed to show rings. Those rings are only explained if electron is therefore acting as a wave, because we know that diffraction is a property of waves, and therefore this explains that electron as a particle is having a wave-like nature. Here I have an example, an application, which is paper 4, example of paper 4 from October, November 16, number 12. The question is shown here. We start by stating an effect, one in each case that provides evidences for wave nature of particle. As we have said, it is the phenomenon of diffraction of electrons beam whereas another evidence about the particle nature of electromagnetic radiation, or the best evidence, was the phenomenon of photoelectric effect. Or photoelectrons. In the next part B, I can recognize that these are some energy levels that refer to the element hydrogen. I can recognize this as having quantum number n equal to 3, 4, and 5. For the emission spectrum associated with these energy levels, on the figure 12.1, mark with an arrow the transition that gives rise to the shortest wavelength. A shortest wavelength corresponds to the highest energy, and the highest energy corresponds to the highest frequency, and this is obtained, of course, by the largest difference between the levels. I meant the transition from level 5 to level 2. Let me remind you that levels from 2 up are recognized as excited levels. In the second part, we need to show that the wave of the transition is given by 4.35 times 10 to the negative 7. This is done easily by remembering that energy emitted during this transition is equal to energy initial minus energy final. Energy initial is E5 minus E2. Which is negative 0.54 minus minus, that's a plus 3.4, and the energy obtained, okay, so 3.4 minus 0.54, and the answer is 2.86. electron volt. Of course, we need to convert it to joules before proving the value or the given value of the wavelength. Remember that to convert to joules, we have to multiply by 1.6 times 10 to the power of negative 19. And the answer is going to be 4.58 times 10 to the negative 19, and this is joules. Also remembering that energy E is equal to hc over lambda, and that's it, we get lambda equals hc over E. And therefore 6.63 times 10 to the negative 34 multiplied by C 3 times 10 to the power of 8 divided by the energy, which is 4.58, 10 to the negative 19. And so we can easily get our answer as lambda. Let's just make sure. I have 6.63, 10 to the negative 34 times 3, 10 to the power of 8, and divided by 4.58, 10 to the negative 19. Yeah, the answer is 4.34 times 10 to the negative of 7. Just to close to the number supposed here. In the next part, I have a direct application on our point here, which is the de Broglie wavelength, where they are asking us to state what is meant by the de Broglie wavelength. The best answer is that to say that moving particles are having wave-like nature associated with a wavelength that is inversely proportional to the momentum of the moving particle or of this particle. Okay, a numerical application later saying that calculate the speed of an electron having a de Broglie wavelength which is equal to the one calculated in the previous part. So remembering that the wavelength lambda is equal to h over mv, which is the momentum, means that the speed v is equal to h over m lambda. And that's it. When I substitute my numbers, you can easily get the speed. The mass of the electron is like 9.11 times 10 to the negative 31 kilogram. Will of course be given in your data booklet multiplied by the wavelength that we previously calculated, which is 4.34 times 10 to the negative of 7. And upon calculating, and the answer is almost 1.7 times 10 to the power over 3 meters per second.